Hello, welcome to Advanced Composites. Today is the second day of this ongoing week, which is the second week of the course. Yesterday we introduced you with all the sign convention for stresses, strains, and we also introduced the notion of a tensor. Further, we explained how stress is a second order tensor, strain is also a second order tensor, because in both these cases the quantities stress and strain are associated with two mutually independent sets of directions. In case of stress, these two directions correspond to the direction of the plane on which the force is acting and also the direction of the force. And in the case of strain, these two sets of directions correspond to the direction of displacement and the direction in which its partial differential is being calculated. We also saw yesterday that the mathematical relationship between stress and strain is through a fourth order elasticity tensor, which is EIJKL. So, now we will further discuss this particular tensor in context of anisotropic materials. Okay. So, what we had developed yesterday was sigma ij equals double summation E I J K L epsilon K L, and here we are summing on 3 indices. So, L equals 1 to 3 and K equals 1 to 3. So, once again here indices I, J, K, L, all of them could assume values of 1, 2 and 3, and 1, 2, 3 are basically axes. 1 could be x axis, 2 could be y axis and 3 could be z axis. Now, if you look at EIJKL tensor, it could have 81 different values. Why? Because we will have 81 different combinations of EIJKL, because I can assume 3 different values 1 to 3, J can assume 3 different values 1 to 3 and so on and so forth. So, the total number of combinations of EIJKL would be 3 times 3 times 3 times 3, and that corresponds to 81. Okay. So, in general this relation between stresses and strains involves 81 different elastic constants. So, for an isotropic material, we are starting with a situation where there are 81 different elastic constants. Okay. So, now we start simplifying this. So, the first simplification we do is based on the fact that epsilon K L equals epsilon L K. Why is that? So, the definition of strain tensor is epsilon K L is equal to del partial derivative of u L differentiated with respect to partial derivative of x k. Okay. So, x k, x 1 would be x, x 2 will be y, x 3 will be z and so on and so forth. So, this is 1 plus del u k over del x L and this entire thing into 1 by 2. Okay. So, this is the definition of strain, and when you, so this comes from mathematics, we will not go into that, and what you find is because of this epsilon K L is equal to epsilon L K, right. So, what that means is that if epsilon L K is equal to epsilon K L, then the number of independent constants in this block K L will not be 9. If this equivalence was not true, then this would be the number of independent constants involved with subscripts k and l would be 9, 3 into 3. But now, if there is a 3 by 3 matrix, then this matrix will be symmetric, which means that there will be 6 different possible combinations, not 9. So, if that is the case, then the number of elastic constants, number of independent elastic constants it comes down to 3 times 3 times 6. So, this is because K L is symmetric epsilon K L is symmetric. Okay. So, that means it is 54. So, all of a sudden the requirement that we have to find 81 elastic constant, it drops down and it comes to 54. Next, look at E I J K L, and this is multiplied by epsilon K L. So, that equals sigma I j. Now, we know from principles of mechanics that tau 1 2 equals tau 2 1, tau 2 3 equals tau 3 2, and tau 1 3 equals tau 3 1. So, essentially what that means is that there are not 6 independent stresses, but rather there are we do not have 9 independent stresses associated with sigma I j, but 6 independent stresses. So, we have already simplified the number of combinations associated with subscripts k l n to 6, and similarly if we find that this also is associated with not 9 independent situations, but only 6 independent situations, because I j relates to sigma I j. Okay. So, the number of constants, so this is I j is related to 6 and k l is related to 6 independent situations. So, number of elastic constants it drops down to 6 times 6 is equal to 36. So, we started with 81, because of symmetry of strain tensor it comes down to 54, and because of symmetry of stress tensor it now comes down to 36. Okay. Let us move further. So, the next simplification is based on principles of thermodynamics. Okay. It is based on principles of thermodynamics. So, before we talk about this, if there are 36 independent elastic constants, then the stress strain relationship would look something like this. So, in this we have a big matrix involving elasticity tensor, and this is epsilon 1 1, epsilon 2 2, epsilon 3 3, epsilon 1 2, epsilon 2 3, epsilon 3 1. Okay. And the elasticity matrix would be E 1 1 1 1, E 1 1 2 2, and then I am not going to write E again. So, the third one will be 1 1 3 3, because this term connects the first row, which is sigma 1 1, with epsilon 3 3. Okay. So, that is why its subscript is epsilon 3 3. And then we have 1 1 1 2, 1 1 2 3, and 1 1 3 1. Likewise, the second row will have 2 2 1 1, 2 2 2 2, 2233, 2212, 2223, 2231, okay, and so on and so forth. So, you can, using this concept, you can develop the whole matrix, you can develop the whole matrix. So, we will just write one more row. So, the next row will be 3311, 3322, 3333, 3312, 3323, 3331, okay. And then we have fourth row, fifth row, sixth row. The sixth row would be 3131, the last element. Now, based on thermodynamic considerations which are related to strain energy density, and the description for this and justification for this has been explained in our introductory course. These are overall 36 independent constants. These are overall 36 independent constants. Okay. So, these 36 constants come down to 21, because based on thermodynamical considerations which we are not going to explain, there are further simplifications, and those simplifications imply that this entire matrix is symmetric. So, this E matrix is symmetric, okay, which means, so if it has to be symmetric, then this number should be same as 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 this, and so on and so forth. Okay. So, a 6 by 6 matrix initially had 36 independent constants, but now because of symmetry, the total number of constants, it drops down to 21. Why is it 21? Because there are 6 independent constants in the first row, 5 independent constants in the second row, 4 independent constants in the third row, plus 3 plus 2 plus 1, and so on and so forth. So, if you add this up together, it is 21. So, this is the final answer. So, finally, we can say that a fully anisotropic material has 21 independent elasticity constants. Okay. It has 21 independent elasticity constants. So, how did we get here? We started with 81 constants. Because of symmetry of strain tensor, it came down to 54. Because of symmetry of stress tensor, it came down to 36, and because of thermodynamic considerations involving strain energy density function, it comes to 21. So, this concludes our discussion for today. Tomorrow, we will continue this discussion, and we will show that the number of elastic constants drops down further if the material was especially orthotropic, which we have discussed what it means yesterday. So, for that kind of a situation, we will make some more simplifications, but if the material is not specially orthotropic and fully anisotropic, then what it means is that there will be 21 independent elastic constants which will relate stresses and strains. So, that concludes our discussion, and I look forward to seeing you tomorrow. Thank you.